you have to come at least once a week, or?
Yes. It's going to be very similar. So next semester is going to be very similar to this semester, where you have to pick a day because we're still trying to social distance. But you're going to have to come in person at least one of those days. How a lot of instructors are doing it is they don't want to keep track of who's coming when, because we can't grade you on attendance. So instead, they're going to have in-person exams instead of online exams. So like you're going to have to be there in person on exam day. You're not going to have that online option. So a little bit different, but. So this week is chapter 7. We already started talking about chapter 7 at the end of last week. So we have the homework and the discussion. The homework is a version that I made starting in chapter 8 and 9. We'll go back to the McGraw-Hill homework so that people can use all of their cool tools like the guided solutions and hints and stuff like that. I did post a chapter 7 homework, or I opened one up, I should say, in McGraw-Hill. It's just not worth points. So you can still see guided solutions for this chapter. It's just not a graded thing. So kind of to review what we talked about last time, we looked at endothermic and exothermic. And so with endothermic, this was heat absorbed, and exothermic is heat released, is the short version of their definitions. So with endothermic, heat absorbed, if you're holding on to the reaction flask as the reaction's happening, heat is going to be absorbed from your hand and you're going to feel it get colder. So this is just a summary of how to tell if a reaction is endothermic or exothermic, depending upon what information you're given. So if you're given the Q value, or if you have to calculate the Q value, you can figure out if it's endothermic or exothermic based off of the charge. So if you get a negative Q value, so your final temperature is less, it cooled down, it absorbed heat from your hand, then it's going to be endothermic. Exothermic, you're going to get a positive Q because heat's being released, so your final temperature is going to be greater than your initial. You're going to feel it warm up. Looking at enthalpy, so this delta H is change in enthalpy. So notice it's the opposite of Q. So if you get a positive delta H, it's going to be endothermic. And if you get a negative delta H, it's exothermic. And we can kind of explain it better using these reaction diagrams that we looked at last class. So in these reaction diagrams, what we have is the reactants always on the left-hand side, and then the products on the right-hand side. So what we're looking at here, the change in enthalpy is the distance from where the products are to where the reactants are. So this is our delta H, here to here. Now if the products are higher in energy than the reactants, we're going to get a positive delta H. So this is going to be endothermic. So this is what it's going to look like in the diagram. The products are higher than the reactants. For exothermic, it's the opposite. So if we have the reactants higher in energy than the products, what we're going to get is a negative delta H. Because if the products are lower in energy, we always do products minus reactants. It's going to be those values. So if we have a low number subtracting a higher number, it's going to get us a negative value. So this is what the reaction diagram looks like for an exothermic. So if you're given any one of these pieces of information, you should be able to tell what type of reaction it is, endo or exo. The last, we didn't talk about too much, what if you're given a reaction equation? So these A, B, C, D's, these are just the elements or compounds in the reaction. Okay, so just arbitrary ones. Because these aren't important to figure out if it's endothermic or exothermic. What's important is where is heat in the equation. So if they have heat, oftentimes represented by like, maybe they'll have 25 kilocals. So these are the two different ways you'll see. You'll either say heat in parentheses, or you'll see a number with kilocalories after it, the units of kilocalories. So either of these represent heat. If the heat is on the reactant side, it's going to be endothermic. Because heat's being absorbed in endothermic. So it's on the reactant side, so it can be absorbed to make the products. For exothermic, we're going to see the heat on the product side. Because remember, heat's being released, so we're going to feel it get warmed up. We feel it get warmed up when the products react. So the heat is going to be coming from the product. That's one of the products because we're feeling that one. So this is the basic summary of how to tell if it's endothermic or exothermic. So what we're going to look at next is we're kind of taking a break from endo and exothermic and moving into Le Chatelier's principle, which has to do with the equilibrium reactions. And so we need to talk first about reversible reactions. We'll talk about equilibrium, and then we'll apply Le Chatelier's principle and do some problems with that. Okay, we forgot my piece. We've been working on this homework, correct? So we did through 23. So 24, looking at those practice problems that we've been working on in class, this is what we're going to work up to today, but we're going to go through some definitions so we can understand how to do this first. And this is the only question on Le Chatelier's principle. 25 and up, those questions have to do with chapter 8. So I'm going to erase this and we're going to look at reversible reactions and talk about equilibrium a little bit so that we can understand how to apply Le Chatelier's principle.
Do you have another one of those?
Yes, I do. So far when we've looked at reactions, we've had products, let me do this. Reactants going to products. So we've seen an arrow, right? So all of this reacts to make this. What a reversible reaction is when it can revert back. Okay, so a reversible reaction, see I'm talking and trying to spell at the same time, does not work. Reversible. You'll see a two-headed arrow. So they can, A and B can go to make AB, but AB might decompose back into its original counterparts. Okay, so this is called a reversible reaction. We don't have all of the reactants going to product and then we're done. It actually goes back and forth. And the example that I used on the PowerPoints was sugar water. So with sugar water, you can actually use glucose instead. For some reason, that one's sticking in my head. So I'll use glucose instead of actual sugar. So this is going to be solid. I'm going to add water to it. And then we're going to get this dissolved. So it doesn't look like anything happened, but something did. Because it's a solid on this side, and over here it's dissolved, it's aqueous. So that's the change. So this is an equilibrium reaction. Or I should say this is a reversible reaction. We'll talk about equilibrium in a minute. So it's reversible because what's happening, and I like to use the example of sugars because if you've ever made Kool-Aid, and I don't think they even do it this way anymore, but you used to have to empty the packet and then go find sugar and put sugar in there too. And what happens if you add too much sugar, you get these solid sugar particles at the bottom that aren't dissolved. Okay, so here's my Kool-Aid with my sugar all aqueous except for a few solid pieces. Now, this would be an equilibrium because what we have is this solid sugar is actually dissolving at the same time that the dissolved, the aqueous sugar molecules are precipitating out. Okay, so what is this? This is called dynamic equilibrium. This is when the forward rate equals the reverse. So I know this sounds confusing, but what's happening is that sugar that you see precipitated out at the bottom, it's not the same sugar molecules that you're going to see 10 minutes later. Because it's constantly dissolving and then new ones precipitating out. That's what this arrow means, going this way because it's the solid's dissolving and the aqueous is reverting back to the solid form. So it's a consistent cycle. And we call this a dynamic equilibrium because that means the forward rate is equal to the reverse rate. The reason we're talking about reversible reactions, why we're talking about dynamic equilibrium, is because when we look at Le Chatelier's principle, we need to have an equilibrium equation. An equation that's reversible. We can't do it, we can't apply Le Chatelier's principle to an equation that isn't reversible. It can only be applied to ones that are reversible. So what is Le Chatelier's principle? I'll leave this bottom part here. Got it? And I always spell his name wrong. I spelled it right on my paper so I could get it today. I always get this E right here. There's the rest of this. There's a little sign there too. Okay. So Chatelier's principle is when we have an equilibrium, okay, when we have the forward rate equal to the reverse rate in a reversible reaction. So when we have an equilibrium, and it's disturbed. And what I mean by disturbed is something changes. So whether it's the concentration that changes, whether the reaction's heated, whether there's a pressure change, something is changed to disturb that equilibrium. And what Le Chatelier's principle says is that it's going to try to get back to normal. So it's going to shift turn back to normal, what's a better way of saying that? Shift to minimize the disturbance. So notice the definition has the words equilibrium in it. So once again, it does need to be an equilibrium equation. Before we look at an equation and apply, let's look at what this disturbance part means. So what do we mean by a disturbance? Well, most common disturbances, there can be others than these three, but these are the three main ones that we see, is a change, so that's what this triangle means. Remember, the delta H was change in enthalpy, so change in concentration. So what this means is we're either adding or removing reactants or products. That's one of the disturbances. So I can write that up here so that you know what these are. They're also called stressors. It's basically just something that's going to affect the equilibrium. Okay, so disturbances or stressors. Change in concentration. So this is when we're adding or removing reactants or products. Right? If we make something more concentrated, we're adding. If we make something less concentrated, we're removing. We also can see a disturbance if we change the pressure. But with pressure, the key with this one is it only affects, I don't know if that's effects or apex, I always get that wrong, gases. So if you have a reaction, equilibrium reaction equation that has no gases in it, they're all aqueous or liquids, changing the pressure is not going to do anything. Okay, but if you have a gas and you change the pressure, for instance, if you increase the pressure and you have a gas, what you're doing is you're trying to push that gas into solution. So you're concentrating that gas in the solution more. And we'll look at an example of that. The last one, temperature. So a temperature change. And what I mean by a temperature change is we're looking at that heat. So it's going to depend where the heat is in the reaction equation. All right, so these are the possible disturbances. Let's look at a reaction we've done before. I think recently, Lab 9, I showed this reaction being done. So the important thing with Le Chatelier's principle when you're applying is, yes, you need a reversible reaction, an equilibrium reaction, but you also need the states. What I mean by states is this a solid? Is it aqueous? Is it a gas? I need to know what it is, because if I change the pressure, Pressure is only going to affect my gases, so I need to know what states these are in. What's the physical state? Now notice, this is something we didn't see in Lab 9. I added heat on the product side. The reason for this is because if you were doing that reaction, you were holding that flask, you would have felt it warm up. Okay, so you feel it warm up, heat's on this side. Just for a quick review, is this endo or exothermic? Heat's on the product side. Exo, when heat is on the product side, it's an exothermic reaction. Now this does not matter for Le Chatelier's principle, but it's just a practice. Because heat is on the product side, it is exothermic. So, let's do some stressors. All right, let's change the concentration. So if I'm doing this reaction, remember I have that solid piece of magnesium and I added HCl to it. Okay, well let's say I add more magnesium. I add more magnesium solid. So I need to figure out what's going to happen. If I add more magnesium, where is the equilibrium going to shift? Because I'm disturbing it now, right? I'm changing the concentration. So Le Chatelier's principle says if you disturb this equilibrium, if you try to change anything, it's going to shift the reaction to try to minimize that disturbance. So it's saying, going over to this magnesium, I just added some of it. So the concentration of magnesium increases. But Le Chatelier, it wants to get back to equilibrium. So that extra magnesium that I just added, it wants to get rid of it. So in order to get rid of it, it's going to shift the reaction now to the right towards the products. Because that's the only way it can get rid of the extra is by making more products to get rid of that extra I added. Okay. Let's look at pressure. So do you want to increase pressure or decrease pressure? Okay, let's decrease. Let's go down because we went up here, we increased, right? So we're going to decrease the pressure. So if we decrease pressure, pressure is only going to affect the gases. So you look in your equation, you look where the gases are. H2 is my only gas. And I just said I'm going to decrease the pressure. What that does is it decreases the solubility of the gas. So it's similar to concentration. This is going down. Right? It's not going to be as soluble because the pressure is not there to push it down into solution. So that means the concentration of H2 has went down. So I'm losing my H2 gas. So which way is the equilibrium going to shift? It wants to replace what I lost, what I took. Taking away is the hard one.
Increase.
So is it going to shift toward products to make more H2 gas, or is it going to shift towards reactants to get rid of more H2 gas? It has to go toward the products. We're trying to either get rid of what we added, if we added extra, or replace what we took. So to replace it, I'm going to have to shift towards the products to make more, to make what was taken. Okay, so this one is also going to be right towards products. If I would have went the other way, like instead of decreasing the pressure, if I would have increased the pressure, that would have said, okay, my H2 gas is now more soluble, the concentration of the H2 gas is higher, I have too much of this. So Le Chatelier's principle is going to say, if you have too much, well, let's get rid of it. How do I get rid of it? You have to go the opposite direction to get rid of. So kind of a good side note would be, if you add extra, it's going to shift away from where you added to get rid of. If you took away, it's going to shift towards what you took. So this one would be left towards reactants.
But it's only in the products.
What do you mean it's only in the products? We affected one of the products, yes. We increased the concentration of one of the products. So since we added extra of it, looking at this left one, right? If we increase the pressure, we increased the amount of H2. So they want to get rid of that amount we increased.
But you add magnesium over here in the equals.
Right, these are all different. So I would never do all of these at the same time.
All right.
Okay, so yeah, sorry, that's confusing. That's why I tried doing it in different colors. So you would never increase and decrease the pressure because that, you know, these are all separate questions. These would each be a different question.
Okay.
So to make it less confusing, let me just erase them as we go so we only see one at a time. Okay, so let's look at temperature. We haven't done a temperature one yet, right? So temperature change. So this is where we're affecting the heat. So whenever you see a temperature change, you're going to look, where's heat? So either you can increase your temperature or you can decrease your temperature. Which one do you want to do? Increase? Okay, so let's increase the temp. So if we increase the temperature, we find where heat is. And we just said increasing. That means we're adding extra heat. So we've disturbed the equilibrium. We're adding some of this. It's like almost like we're increasing the concentration of heat, if you will. So we have too much heat and we need to get rid of it. So which way are we going to shift to get rid of it? Towards products or towards reactants? Towards reactants. So we want to shift away from where we added the extra. And away is towards the reactants in this case. So we're trying to get rid of that extra heat. So, here's this. Move this guy up a little bit. Now these were all just random examples. Let's apply them to number 24. So it's the same equation. So that's why I'm leaving this equation up. And we already answered the first one, but let's answer it again, I guess. So each of these, A, B, C, and D, these are all separate occurrences. So they'd be separate questions. Okay, we're not doing all of these at the same time. So looking at A, we're adding solid magnesium to the reaction. So find solid magnesium and we're adding it. Right, we add this, it's going to shift to get rid of the extra, so to the right. Okay. Now a separate one, increasing the pressure. Left. So to increase pressure, you're looking at which one of these reagents? Which one is changing? Increasing pressure only affects? It only affects gases, so we're looking just at H2. And we said we're increasing, so that means it's going up.
But if you go increase, aren't you going right?
Yeah, you want to go away, so you're right, to the left. Yep. Towards reactants to get rid of that extra. Now here's a weird one, or different wording. C, we haven't looked at this one yet. Increasing the molarity of HCl. So you need to know the definition of molarity. What's molarity? It's moles over liters, but what is it? Is it a pressure, a temperature, a concentration? It's a concentration. That's what we learned in chapter 6. We learned like 10 different ways to calculate concentration. Molarity was one of those ways. So it's saying you're increasing the concentration of HCl. So you find where HCl is, it's on the reactant side, and we're saying, okay, we're adding extra of it. It's going up. So which way is the reaction going to shift? You're right. Yeah, to the right. We want to get rid of it. We have extra of it. We've disturbed the equilibrium. We want to get back to normal. So to get rid of it, we shift to the right to make more products. Okay, so right towards products. And last one, we did that one intuitively. Last one is increasing temperature. I think we just did that one a minute ago. But do you remember?
We're gonna go up,
We're gonna go
and go to the,
with the reactant.
Yes, left towards reactants. Okay. Questions on this so far? So now I'm going to do one more, and we're not only going to look at which way is the equilibrium shifting, but we're going to see what we're making more of. So I know that sounds confusing, so let me just write the question and try to explain it a little bit better. So this time I'm going to if I cool it down, say cool down the reaction, what happens to HCl? What I'm asking is that going to increase or decrease? So I'm going to take it a step further. So let me get rid of this arrow. So now I'm cooling down the reaction, cooling down the temperature. So what is that going to affect?
The product will be
Cooling down is changing temperature, so which one of these is decreasing? Because cooling down means decreasing.
so the product.
The products, but most specifically the heat, right? So we're saying this heat is going down, we're cooling it down.
so hydrogen.
So let's take it step by step and see, okay, if I took that away, which way is the reaction shifting? Is it going to go towards products or towards reactants? So I took away, if I took this away, we're going to want to replace what I took. So if we want to replace what I took, which way does the reaction have to shift? If I want to make more of that, which direction do I have to go? Let's put it this way. Say the reaction shifts this way. What's happening if the reaction shifts this way is I'm using all of these, so I'm taking some of all of these away to make more of the reactants. Okay. But if it shifts this way, what I'm doing is I'm removing some of these or lowering these concentrations to make more of the products. So right now, since I decreased the heat, since I took some of that away, what the equilibrium is going to do is it's going to try to replace what I took, right? So it's going to have to go towards the heat, towards the products. But what we're trying to look at with this question is, okay, yes, I took some of this away. I know that it's going to shift towards what I took to replace what I took. But when it does that, what happens to, in this case, specifically HCl? So this HCl here, since I shifted towards products, am I going to increase the amount of HCl I have or decrease? It's going to have to be decreasing because,
Because losing.
right, you're losing it. We're taking these, they have to be used to make more of the products. So that's going to actually decrease my HCl. It's going to decrease both my products. So if I would have asked about magnesium, it's going to do the same thing. It's going to decrease my magnesium. So when, this is just the bigger picture, when the reaction shifts to make more, it's because we're losing some of this. All right, so let's try. just remove a different one. Remove magnesium, what happens to the hydrogen gas? So you have to take it step by step. You have to say, okay, if I take one of this way, which way is the reaction going to shift? And then look at the hydrogen gas. So we're taking away magnesium solid. So find magnesium solid, and we said taking away, it means it's decreasing. So if I take some of this away, which way is the reaction going to shift? Towards it or away from it?
Change the concentration.
It's changing the concentration. We're decreasing the concentration.
And shift towards the product, I mean, the real.
It's gonna,
It is going to shift. So I took this away, so I want to make more of it. So it's going to shift towards what I took. So it is towards the reactants. So if it shifted towards the reactants, what's happening to H2?
it's gonna go up.
Do you think it's going to increase?
Increase.
So if we shift towards the reactants, it's because we're using all of these to make more of the magnesium. So if I use some of the H2, is the H2 going to increase or decrease if I'm using it? It's going to decrease, so let's separate this out. Let's write this as two separate reactions. So equilibrium reaction, it means that we can go this way. So that's one direction. But it's also saying the reverse is true. H2. So it's saying these two reactions are going on simultaneously. Okay? In the top reaction, my reactants are magnesium and hydrochloric acid. In the bottom, my reactants are different. So we're saying that so when we take these reactants, because that's the way we're going, right? These are our reactants going over there, in this case. You know, I mean, yeah, it's kind of confusing, but. So if I were taking these three, and the reaction was going this direction, I'm making more magnesium. That was the goal, because the magnesium went down. So I'm going to go this direction to make more magnesium. In order to make more magnesium, I have to use these up. So if I'm using these, all of them are going to be decreasing. So that's going to go down, that's going to go down, that's going to go down. So I'm using it to make more of this.
Okay.
Okay, so you're kind of just seeing, okay, which way am I going? And whichever way you're going, the reagents on this side of the arrow are going to be increasing. The reagents over here are always going to be decreasing. So think of it like a normal reaction, right? I'm using these up to make more of this. So these are all going to decrease, these are both going to increase. If I was going the other direction, these are going to decrease, and this is going to increase. So that's why we're trying to figure out which direction are we going. Once you figure out the direction, these are all going to decrease, these are all going to increase.
But when you're decreasing this, you're decreasing the other part too.
Yes, it is decreasing the other parts too. Yep.
Okay.
So we're not just losing some of the hydrogen gas, we're also losing some of the concentration of the magnesium chloride and some of the heat. So that's the price of trying to get it back into equilibrium. All right. So that's all we're going to cover today. What we're going to look at